When solid iron reacts with hot steam, the result is iron oxide and a release of hydrogen gas. If we translate that physical reaction into chemistry, we get this skeletal chemical equation. There is an immediate problem with how this is written. On the left side of the arrow, we start with 1 iron atom. On the right side, we end up with 3. We are somehow creating mass out of thin air, which directly violates the law of conservation of mass. To fix this, grab a pen and a piece of paper. Over the next 5 minutes, we are going to walk through a strict 7-step method to balance this exact equation. The goal is simple. We have to mathematically balance the scales of nature, ensuring the total number of atoms on the left perfectly matches the right, without ever altering the chemical identities of the substances themselves. Step 1 is to draw protective boxes around every single chemical formula in the equation to establish strict boundaries. This is the golden rule of balancing. You cannot change anything inside these boxes. The subscripts, those small numbers attached to the elements, are locked. We can only place multiplier numbers, called coefficients, on the outside. For step 2, we take our initial inventory. We need to tally exactly how many atoms we have on the left-hand side, the reactants, versus the right-hand side, the products. We build a simple 3-column table below our equation to track our starting inventory. Iron is out of gallons, 1 on the left, 3 on the right. Hydrogen is stable at 2. Oxygen is heavy on the right, 4, compared to 1 on the left. Now that we have defined the exact numerical scale of the problem, we need a rule to determine which of these imbalances to address first. Step 3 is to target the most complex compound first. In this equation, that is the iron oxide on the right. Inside that compound, we select the element with the maximum number of atoms, oxygen, which has 4. To balance oxygen, we place a coefficient of 4 in front of the reactant water molecule. The tally chart updates. Oxygen is perfectly balanced at 4. But this causes collateral damage. We now have 8 hydrogen atoms on the left. For step 4, we target the solitary hydrogen gas on the right. By placing a coefficient of 4 in front of it, we multiply 4 by 2, equalizing the count at 8 hydrogens on both sides. Step 5 addresses the final unbalanced element, the singular iron atom on the left. We place a coefficient of 3 in front of the reactant iron to match the right side. The tally updates to 3 and 3. This process is known as the hit and trial method. It is a deliberate chain reaction. You adjust a coefficient, audit the disruption, and readjust until perfect mathematical equilibrium is achieved. Step 6 is the final audit. We perform a complete verbal sweep of the equation to verify our tally. We confirm 3 iron atoms, 8 hydrogen atoms, and 4 oxygen atoms are present on both sides of the arrow. The mass is perfectly conserved. Finally, step 7. The math is correct, but the equation lacks physical reality. We must define the states of matter. We append standard state symbols, a lowercase s for the solid iron and solid iron oxide, and a G for the hydrogen gas. Notice the reactant water also receives a G for gas, instead of an L for liquid. This specific symbol indicates that the reaction requires water in the form of hot steam to actually work. These symbols clarify the specific physical environment required for this reaction to take place, providing a complete account of the chemical event. Now we can remove the training wheels. We drop the boxes and the table, leaving us with the final balanced chemical equation. The result is a precise accounting of every atom involved, ensuring that no matter has been created or destroyed during the process. To lock this in, test your new skills right now on a simpler equation: magnesium burning in oxygen to form magnesium oxide. Remember your core rules before you start. Draw your protective boundaries, make your initial tally chart, and never alter a subscript. This 7-step process allows you to handle even the most complex chemical reactions with mathematical certainty.
Welcome to my study buddy. Remember to like, share, subscribe, and comment.